two RDS features look nearly identical on paper. One keeps a silent standby in another zone and swaps to it automatically when the primary goes down. The other also keeps a copy, but that one actually answers read queries. Reach for the wrong one and your architecture breaks in a way that's hard to debug. That's the setup. This is Cloud Architect Path from Stack Lessons. By the end of this video, you'll know exactly when to reach for multi-AZ, when to reach for read replicas, and when Aurora changes the whole conversation. This is the most confused near-identical pair on the exam, so we're going to take it slowly and make the distinction airtight. Back in episode 1, we flagged this exact pairing as the canonical confusion on this exam. Two answers both look valid, and a single qualifier word in the question quietly decides which one is right. Today, we turn that from a warning into a rule you can apply without hesitation, and then we extend it all the way into Aurora. 5 terms anchor everything in this episode, so let's lock them in now. An Aurora replica is a read-only instance that shares the same underlying storage as the writer, which keeps lag under 100 milliseconds and makes it a built-in failover candidate. Aurora Global Database stretches across regions, one write region, up to 10 read-only secondaries, with replication that typically completes in under a second. Aurora Serverless v2 is the current generation that adjusts compute automatically as your workload shifts. RDS Proxy sits in front of your database and pools connections so your application isn't hammering the instance directly. And an Aurora Capacity Unit, or a CU, is the increment serverless v2 scales in roughly 2 GB of memory per unit. Here's the mental model that unlocks everything. Amazon Web Services gives you 2 independent dials. Multi-AZ is the availability dial. It decides how quickly you recover when a zone fails. Read replicas are the read performance dial. They decide how much read traffic you can serve. These are not 2 options you pick between. They're 2 separate controls, and a serious design turns both. Megacorp is holding multi-tenant financial data for more than 300 enterprise clients in a single PostgreSQL cluster with no cross-region replication. That's a single point of failure. One availability zone goes dark, and every one of those clients goes down with it. But look closer, and there are actually 2 separate problems hiding inside that one design. One is availability, surviving a zone failure. The other is read scaling, handling all the reporting load those clients generate. Solving them means knowing exactly which tool answers which problem. Let's start with multi-AZ. As we defined it in episode 1, this is about availability. RDS provisions a synchronous standby and a second availability zone, and it's kept perfectly in step with the primary. Every write lands on both before it's acknowledged. When the primary fails, RDS handles the failover automatically. It repoints the shared DNS endpoint to the promoted standby, so your application reconnects to the exact same endpoint with no configuration change at all. Typical failover completes in 60 to 120 seconds. Think of the standby as a spare tire mounted on the back of the vehicle. It's inflated to the same pressure, continuously kept ready, synchronized with the tires you're actually driving on. When one blows out, the spare swaps in automatically and you keep going down the same road. But here's the part people miss. You never drive on that spare while all 4 tires are fine. You can't use it to carry extra passengers. It exists for one moment and one moment only. And this is the single most important line in the entire lesson, straight from the Amazon Web Services documentation. A multi-AZ deployment has one standby that provides failover support, but doesn't serve read traffic. Read that again. It doesn't serve read traffic. The standby is invisible to your application during normal operation. Any answer that suggests reading from it is wrong before you even finish the sentence. One detail worth knowing: in the classic deployment, that synchronous replication happens down at the EBS storage volume level, not up in the database engine. So even if the primary's database process crashes, The storage infrastructure keeps replicating independently. When someone says multi-AZ without qualification, they mean this classic single standby deployment, where the standby is not readable. That newer variant, the multi-AZ DB cluster deployment, adds two standbys that can actually serve reads, unlike the classic single standby model. That distinction is worth seeing side by side. On the left is the classic multi-AZ DB instance. One standby in another zone, synchronous replication, standby not readable, failover in 60 to 120 seconds. When the exam just says multi-AZ, this is what it means. On the right is the newer multi-AZ DB cluster. That one has a writer plus two standbys spread across 3 zones using semi-synchronous replication. And here the standbys can actually serve reads with failover under 35 seconds. It's a different product here on modern MySQL 8.0 28 or later, and PostgreSQL 13.4 R1 or later. The takeaway, unqualified multi-AZ means the non-readable standby on the left. Now the other dial, read replicas, built for read scaling. Replication here is asynchronous, which means a replica reflects a slightly older state of the data, eventual consistency. Each replica has its own endpoint, and every one of them is fully readable. You can run up to 15 replicas for most engines, though RDS for Oracle caps at 5. They can even sit in another region. But here's the critical attribute. If the source fails, a replica does not promote itself. Promotion to a standalone primary is a manual, deliberate action. There is no automatic failover. Picture a master ledger that only the head accountant can write in. A read replica is a photocopy of that ledger. Analysts can read as many photocopies as they like all at once without ever bothering the head accountant. The photocopies are always a little behind because that's asynchronous replication. And if the head accountant suddenly disappears, one photocopy can be elevated to become the new master, but only if a manager makes that deliberate call. It never happens on its own. The documentation nails both attributes in one breath. A read replica allows only read-only connections, and RDS uses asynchronous replication to update it whenever the primary changes. So there's your 2-word summary, read-only and asynchronous. Hold on to that, because it's half of every read replica question you'll face. Let's lock this in. Multi-AZ is synchronous. The standby is not readable, failover is automatic, and it happens on the same endpoint. A read replica is asynchronous, it is readable, promotion is manual, and there's no auto failover. One protects availability, the other scales reads. Keep those two firmly separate in your head, because the exam is about to try to blur them. So here's the recurring wrong answer, the one that shows up again and again. Root reads to the multi-AZ standby. It is never correct. Not sometimes, not under certain conditions. Never. The standby serves no traffic. The moment you see an option that sends reads to a multi-AZ standby, cross it out and move on. Let's work a real scenario. Reporting queries are saturating the primary's CPU. Option A says root reads to the multi-AZ standby. Gone immediately, because the standby isn't readable. Option B, vertically scale the primary, is costly and still doesn't isolate the reporting load. Option D, disable multi-AZ to free up resources, throws away your availability to solve a performance problem. That's the wrong trade entirely. Option C, add read replicas for reporting, is the answer. The replicas absorb the read volume while multi-AZ keeps protecting availability completely independently. And Amazon Web Services doesn't leave this to interpretation. Their own documentation says it plainly. Unlike a read replica, a standby replica can't serve read traffic. If applications require more read capacity, you should create or add additional read replicas. That's the answer key. written by the people who write the exam. Need more read capacity? Add replicas, not the standby. So what does the real design look like? Both together. In the center is the primary, handling reads and writes. Directly below it sits the multi-AZ standby in a second zone, connected by synchronous replication, that's your availability, and notice it's marked not readable. Then, spreading out to the sides are the read replicas. One handles reporting, another handles analytics, both fed by asynchronous replication. The orange path solves availability. The green path solves read scaling. Neither interferes with the other, and Megacorp's cluster now survives a zone failure while its clients hammer the replicas with reports. Here's the framing that practitioners have battle-tested for years. Multi-AZ is your insurance policy. You pay for it and hope you rarely need it, but when a zone fails, it saves you. Read replicas are your performance optimization. They make the system faster every single day. Insurance and optimization are not competing purchases. Real production databases carry both. Now, let's raise the ceiling with Aurora. At the top sits the writer, but the real magic is underneath it. Aurora stores your data as 6 copies spread across 3 availability zones, 2 copies in each zone. Every write needs acknowledgement from 4 of those 6 storage nodes, a write quorum. What that buys you is remarkable fault tolerance. Aurora keeps accepting writes even if it loses 2 copies, and keeps serving reads even if it loses 3. And this durability lives entirely in the storage layer, present even when your cluster has just a single compute instance. This is the point that catches people. The 6-copy, 3-zone redundancy is a storage architecture fact, not a compute configuration you have to turn on. A minimal Aurora cluster with 1 writer and 0 replicas already stores 6 copies across 3 zones. Adding compute replicas gets you read scaling and faster failover, but the durability was there from the very first instance. Here's why Aurora replicas behave so differently. Traditional RDS replication is like mailing copies of your notes to colleagues in other offices. There's delay, and copies can drift out of sync. Aurora's shared storage is more like one live whiteboard projected onto a screen in every room at once. Every Aurora replica plugs into that same underlying volume, so nothing is copied between compute nodes at all. That's also why adding a replica takes minutes instead of hours. There's simply no data to transfer. The new instance just attaches to the volume that's already there. Because all Aurora replicas read from that shared volume, they return the same data with minimal lag. Amazon Web Services puts the number at typically much less than 100 milliseconds after the primary writes an update, often just 10 or 20. And you can attach up to 15 Aurora replicas to a single cluster, each one both a read endpoint and a potential failover target. These two sound alike, but they're architecturally different. On the left, an Aurora replica shares the cluster's storage volume, so its lag is typically under 100 milliseconds, and if the writer fails, it's promoted automatically with no data loss. It serves, reads, and acts as an HA failover target at the same time. On the right, a classic RDS read replica is a separate copy fed by engine-level asynchronous replication. Its lag can stretch to seconds or minutes, promotion is manual with possible data loss, and it only scales reads, availability stays multi-AZ's job. Same word, replica, very different machinery underneath. And this is the nuance that trips up engineers moving from RDS to Aurora. In standard RDS, the availability standby and the read replica are 2 separate feature families. In Aurora, a single replica does both jobs. So you rarely bolt on a separate multi-AZ standby. The Aurora replicas already give you failover targets and read endpoints in one. Aurora deliberately blurs the sharp line we spent the first half of this video drawing. Quick checkpoint. In standard RDS, availability and reads are separate tools, Multi-AZ for one, read replicas for the other. Aurora fuses them into a single replica type, sitting on top of that shared 6-copy storage. Next, let's extend Aurora across regions, and then tune it for cost and for connections. Remember Megacorp's original sin, no cross-region replication. Aurora Global Database is the fix. You get one primary region where all writes happen, plus up to 10 read-only secondary regions. The replication runs on dedicated storage-level infrastructure, not log shipping, with latency typically under a second across regions. Each secondary cluster can hold up to 15 Aurora replicas for local read scaling. When a question asks for cross-region disaster recovery or globally distributed reads on a relational database, this is your answer. In Amazon Web Services' own words, an Aurora global database consists of one primary region where your data is written, and up to 10 read-only secondary regions with replication latency typically under a second. That sub-second figure is the headline. It's what makes Aurora Global Database the tightest cross-region option for a relational database. Now a distinction the exam tests directly. There are two ways to move to a secondary region. On the left, a planned switchover, deliberate, say for region maintenance. It synchronizes the secondaries first, so your recovery point objective is 0. No data loss. Use it for controlled migrations. On the right, an unplanned failover reacts to an actual region outage. Recovery time here is in the order of minutes, and your recovery point is typically measured in seconds. And watch this carefully. That's not sub-second recovery. The sub-second figure was replication lag, not recovery time. Don't let a question conflate the two. Straight from the documentation, for Aurora Global Database, recovery time can be in the order of minutes, and the recovery point is typically measured in seconds. Memorize that pairing. Minutes for recovery time, seconds for recovery point on an unplanned failover, and 0 data loss only on a planned switchover. Aurora Serverless v2, and note that v1 reached end of life on March 31st, 2025. So v2 is the current supported product, scales compute automatically in increments as small as half an ACU, reacting to real CPU, memory, and network load. Each ACU is roughly 2 GB of memory with matching CPU and networking. It ranges from 0 ACUS, which means auto pause, all the way up to 256, and crucially, it scales without dropping your active connections or open transactions. Think of a provisioned Aurora cluster as a car engine locked at a fixed RPM, whether you're coasting downhill or climbing a steep grade. You pay for full capacity even when you're barely moving. Serverless v2 is like a modern electric motor that continuously adjusts its output in tiny increments as the road changes. Always just enough power, no sudden lurches, no over-provisioned waste. That's why the exam pairs it with variable and unpredictable workloads. Finally, connections. RDS Proxy is a managed, highly available proxy that sits between your application and the database. It maintains a connection pool and multiplexes many application requests onto a small set of persistent database connections. The canonical use case is Lambda, hundreds of concurrent functions each opening their own connection and blowing past the database's connection limit. And there's a second benefit. During a failover, the proxy holds connections at the same endpoint and quietly routes them to the new primary, cutting average failover time from about 24 seconds down to about 3.1. Look at the difference. A direct connection to the database averages around 24 seconds to recover during a failover. Put RDS Proxy in front, and that drops to about 3.1 seconds, roughly an 87% reduction. The proxy queues in-flight requests and reconnects to the new primary before your clients even need to re-resolve DNS. When a scenario demands the fastest possible failover, that's your lever. Without the proxy, imagine 500 Lambda functions each walking straight up to the database and knocking on the door. But that door only allows 200 connections. They pile up and the database starts refusing them. RDS Proxy is the hotel concierge at one front desk who greets all 500 guests and routes them through a small set of 50 permanent reserve lines. The database only ever sees 50 connections, no matter how many guests arrive. Let's turn all of this into a keyword drill. When you read high availability, failover, or in region resilience, reach for RDS Multi-AZ. When you read scaling, reporting, or analytics offload, that's read replicas. When you see cross-region disaster recovery or sub-second replication, it's Aurora Global Database. A variable or unpredictable workload points to Aurora Serverless v2, and a Lambda connection storm or a need for faster failover points to RDS Proxy. Identify the goal in the question first, then the feature falls right out. Carry these forward. The multi-AZ standby is never readable. Read from the standby is always the wrong answer. Read replicas are asynchronous, readable, and promoted manually with no auto failover. Production designs use both together, multi-AZ for availability, replicas for read scaling. Aurora's 6-copy, 3-zone durability is automatic and architectural, and global database is your cross-region DR answer, with recovery time in minutes and recovery point in seconds. Serverless v2 handles variable workloads, and RDS Proxy handles Lambda pooling and faster failover. Now let's see how well all of that landed with a quick 5-question quiz. Let's test what you've learned. Question 1. An RDS PostgreSQL primary is running hot because the analytics team hammers it with reporting queries. Multi-AZ is already enabled. How do you relieve the primary without sacrificing availability? Is it A, point the analytics tool at the multi-AZ standby? B, add one or more read replicas and point analytics at them? C, disable multi-AZ to free up standby resources? Or D, vertically scale the primary to a larger instance? Lock in your answer before I give it away. The right call here is B. The multi-AZ standby serves no read traffic at all, so A is impossible. Disabling multi-AZ throws away your availability, and scaling up is costly and doesn't isolate the load. Read replicas absorb the reporting queries while multi-AZ keeps protecting availability completely independently. Question 2. An application needs automatic failover for its RDS MySQL database if the primary zone fails, with no manual intervention at all. Which feature provides this? A cross-region read replica that can be promoted. B, multiple read replicas in different availability zones. C, Aurora Serverless v2 auto pause. Or D, an RDS multi-AZ deployment. Think about which option requires zero human action. The right call here is D. Read replicas, no matter how many you deploy or which zones they sit in, require a deliberate manual promotion. There's no auto failover. Only multi-AZ automatically promotes the standby and repoints the endpoint with no human involvement. Question 3. A financial platform on Aurora PostgreSQL must survive the complete failure of its primary region and resume in another region within minutes, with data loss held to seconds. Which solution fits? A, Aurora Global Database with a secondary region. B, RDS Multi-AZ across 3 zones. C, 15 Aurora replicas in the primary region. Or D, Aurora Serverless v2 with maximum ACS. Run the keyword rule before you answer. The answer is A. The keyword is cross-region. Multi-AZ and replicas within the primary region all die when that region dies, and Serverless v2 is about scaling compute, not surviving a region. Only Aurora Global Database replicates across regions, giving recovery time in minutes and recovery point in seconds. Question 4. A serverless API on Lambda scales to 400 concurrent executions during spikes. Each function opens its own connection, blowing past the RDS connection limit and triggering database errors. What's the best fix? A. Enable multi-AZ to borrow the standby's capacity. B. Create more read replicas to spread the connections. C. Add RDS proxy in front of the database. Or D. Increase the instance size on every spike. Got your pick? Let's see. If you said C, well done. The standby can't take connections and read replicas don't solve a connection storm on the writer. Bumping instance size is a costly band-aid. RDS proxy pools and multiplexes those 400 Lambda connections onto a handful of persistent database connections with no code changes at all. Last one, a company runs a globally distributed application with Aurora Global Database. A planned regional failover is scheduled during a maintenance window. Which recovery characteristic applies to a planned switchover compared to an unplanned failover? A. Both planned and unplanned failovers guarantee zero data loss. B. A planned switchover achieves zero data loss, while an unplanned failover may lose seconds of transactions. C. Planned switchovers take longer than unplanned failovers because they require manual intervention. Or D. Unplanned failovers achieve zero data loss because Aurora buffers writes automatically. Run the decision rule from earlier before you answer. This one is B. A planned switchover lets Aurora coordinate the handoff cleanly. Nothing is lost, so the recovery point objective is 0. An unplanned failover has to act immediately without waiting for replication to finish, which is why the recovery point objective is measured in seconds, not 0. And relational resilience, RDS Multi-AZ, read replicas, and Aurora is sorted. If you want the rest of the Cloud Architect path without searching, subscribe and YouTube handles it. Tell me what clicked and where I lost you. I read all of it. Suggestions for the next course are always welcome. Just name the exam. And if anything about the pace or the look would work better, let me know. Thanks for watching. See you soon.